All right, next door, can you hear me? Say that again, can you hear me? Yeah. Thank you. Okay. All right, so just before we get started, so you would have seen the message I sent out on Friday. Your first class test is going to be held this Saturday. So it's going to be held from 9:30 till 10:30 in the Tattersalls Willsmore lecture theatres, which are over in chemistry. Everyone know where they are? Yeah, if you just look at the map if you don't, okay? So they're over there. So the test is going to start at 9:30 on the dot and will go for an hour. If you can't make the test, you need to apply for special consideration, and if it's approved, you'll resit the test next week and I will let you know when and where. All right, but if you can't make it this Saturday, make sure you get your special considerations done by the following Friday. If I get them after that, then I need to reallocate the marks to the other assessments. Now, I've uploaded a sample test, right, which basically shows you the number of questions, the type of questions, except for the last question, and the level of difficulty. The main thing is the test will only cover the first 3 weeks of lectures, so up to what you covered in the practical classes last week. Right, so what we covered in the lectures last week and what you're covering in the practicals this week will not be in the test. That includes the last question, okay? All right, so basically this thing's going to be an hour long and it's going to have seven questions, okay? So there'll also be a table on the front with the practical classes. So if you just tick or circle your practical, that makes my life much easier when I'm trying to hand the test back to you after they've been marked, because you'll get them back during the practical classes, okay? Right, okay, let's have a look. All right, so first question is going to be something to do with limits of a function of single variable. Okay, what's this? What's going on here? Second one, limit of functions of two variables. You know the deal here. Either you find two directions, it doesn't matter, or you use polar coordinates and show that it always exists. Question 3 will be something to do with L'Hopital's rule, another limit thing, but function of a single variable, but using L'Hopital's rule. Question 4 is basically vector functions, derivatives, so you know, velocity's first derivative position, acceleration's second derivative position, speed is the norm of the velocity vector. Question 5 is going to be one where we find partial derivatives and then the equation of a tangent plane. Right? So what's this one? You've got to find all the partial derivatives, then find me the equation of a tangent plane. Next one's something to do with Jacobians, right? So, remember if it's square, there's always a Jacobian matrix. If it's square, only if it's got the same number of independent and dependent functions, that sort of thing. So this one's, you see it's got function of 3 variables, but it only has two components. And then the last question, again, this will only cover the first 3 words, so it won't cover it'd be something you haven't seen before. It's basically just testing your understanding, right? So it's not going to be something like a couple of the last questions on the practical sheets, which are like really heavy algebra and that sort of thing. It's more designed to test your understanding of what we've been doing, but it will cover something that we've done in the first 3 weeks, right? So up to last week in the practical classes. I've uploaded solutions as well, okay? Obviously solutions for the first 6 questions, and then of course, as I say, the 7th one's going to be something you haven't seen before. You'll get the formula sheet as well. You will get the entire formula sheet, but most likely for test 1, basically mostly you will be using the last page. So remember, I've designed it so you can rip off the last. I've made this table of derivatives and integrals the last page, so you can rip it off and because that's probably the page you're going to use the most. The rest you will get the whole formula sheet, but the rest of it's not really going to be useful for test 1 because most of it starts from what we're covering this week, right? That's where it sort of becomes useful, okay? All right, are there any questions with anything about the test this week? Anything at all? Yes? The formula sheet will be attached to the test paper, right? So it'll be attached to the back. You can rip it off, just do your best to save the staple, but I provide it, you don't provide your own. Are there any other? Yes? Calculator bearing approval stickers allowed. Just make sure it's got a sticker on it. You can bring spare calculators if you wish, right? You can bring 47 spares if you wish. As long as every single one of them's got a sticker on it, I could care less. Right? But they've all got a sticker. Remember, under no circumstances, even if your calculator dies, can you use your phone. Right? You're not allowed to even touch your phone during the test because we'll immediately assume you're trying to use it to cheat. Right? So make sure your calculator's got working, right? And maybe put a battery in it. Most scientifics only take 1 AA. It's not going to break the bank to put a new battery in it. Right? But you can bring spares, but they've all got to have a sticker. Yes? Officially, you're meant to do it in pen. Now, for the final exams, they can be quite harsh on that. You can do it in pen. Personally, I don't care, but for the final exam, you will have to do it in pen. So, do it in pen. Right? But for the tests, I really don't care. Right? I'm not supposed to say that. Personally, I do all my maths in pencil. Right? So, I've always done it. So, yes?
Does the colour of the pen is it specifically black?
No, I don't freaking care. As long as I can read it, if you want to... Well, that comes to the next thing, right? One thing I should mention before you start going out buying exotic pen colours is that there will be 2 versions of the test, right? Because we're going to be in Tattersalls and Willsmore and it's going to be full, right? So people will be sitting next to each other. There will be 2 versions of the test. They'll be the same difficulty, just changing numbers, basically, right? But one will be printed on white and one will be printed on something other than white. Right, so yellow or something like that. So don't bring a light coloured pen, right? So don't bring a yellow pen, and then because when you try and do it on yellow, get something dark, that sort of thing. If you do have an issue with your eyesight and don't like doing it on white paper, just tell us when you rock up for the test and we'll rejig it. It's basically so if 2 people sitting next to each other, they have different test papers. Right, slightly different test papers. So one will be white and one will be not white. Okay? Are there any other questions? Anything at all about the test this week? Yes? Unfortunately, because it's only an hour, and I mean, it's a lecture venue like this. So if you're sitting where you are, for example, right, you are going to annoy a ton of people. So no, I'm afraid not. And go to the toilet beforehand. All right? But no, because of the nature, because we're all squashed in, when you do your final exams, you're in proper venues and spaced out a lot better. But this one only an hour, no. Sorry. Yes. Yeah, as long as for the final exam, when you do your final exams, you're allowed to bring a water bottle as long as it doesn't have a label on it. For the test, it's fine, right? But as long as it's, you can. Yes. Short answer, yes. I don't care, right? No food though. And obviously you're not allowed to have your phone on you. And the other thing is, if you have a watch that we can't tell from a distance is not a smartwatch, you'll have to take it off as well. Okay? Any other questions? Yes?
Does the water bottle and pencil case have to be transparent?
For the final exam, yes. For this, okay. Right? I mean, there's going to be invigilators in the room. We know what you're doing. Right, if you've got notes in there, we know what you're up to, right? And the invigilators will, for the class test, they basically have a zero tolerance policy. You touch your phone or we think you're cheating, kick you out, give you 0, no questions asked. All right, so, usually my scary speech at the beginning is enough to frighten everyone off. So, but yeah, look, for the final exam, they will be it's got to, if you have a pencil case, it's got to be clear. If you have a water bottle, it's got to be clear and it doesn't have a label on it. For the class test, I'm not so pedantic, right? Everyone sort of does the right thing, so, yeah. Yes?
Can you take your bag to the test?
Yeah, that'll be fine. You can either leave it at the front or just leave it under your desk. As long as you don't touch it during the test, I'm happy. Anything else? Any other questions? Up till the end of week 3 lectures. So what you covered in the prac classes last week. So what we covered in the lectures last week and what you're covering in the pracs this week will not be in it, including the last question. Okay? Any other questions? All right, anything at all? All right, so for the, do have a look at the sample test. You are welcome to ask for help with the sample test from your practical classes this week. You can ask my demonstrators don't have a copy of the sample test, but if you bring it along or show it on your phone or whatever, you're welcome to ask them for help. And remember that I have consultation. Sorry. Remember that I have consultation this week from 9 till 12 in my office if you do need some one-on-one help. All right. Any other questions with the test? No? All good? Okay. Again, I should have put, unfortunately, because of the size of the class, we don't have a choice about doing it on the weekend, unfortunately. You can't find enough venues, big enough venues to do it during the class. I also should apologise for those who's doing 101-2 as well. All right? I know there are a few of you. I understand your test is straight after the 101-1-1. Now, normally what we used to do was that, because when you go, or most of this class, those of you who aren't doing 101-2, when you do 101-2, what you'll find is this class flows, right? As in what I mean by that is the topics sort of, it's a logical, what's the word I'm looking for? The topic is all one thing, it's all calculus, basically. But 101-2 is quite disjoint. Right, you do a bit of linear algebra, then you'll do sequences and series, then you'll do, what else is in there? Laplace transforms and it's like a separate topic. So what we used to do in 101-2 was 101-2 had a mid-semester exam and a final exam. And this had 2 class tests and a final. I designed it that way so that they wouldn't clash. Right, but the lecturer for 101-2 likes the way I do it. And yeah. So I do apologise. It's not my fault. I was first. Right? So I've been having tests in weeks 5 and 10 for several semesters. I was first, so don't blame me. And I do apologise for that. And I know the weekend's hard. If you've got to look, I understand there are people who work or sport. I mean, when I studied full-time, I worked part-time. I know what it's like. Right? If you can't make it, the special consideration people are quite understanding about weekend tests. So, if there's some reason you can't do it, I can't guarantee it, but I'm almost certain that your special consideration will be approved, right? And you'll sit it the following Friday, okay? Any other questions? No? Okay. All right, so do have a look at the sample test and things like that. Remember, you can ask questions during your practical classes, and I've got consultation as well if you need it, okay? All right. Now, what we're going to cover this week is something I elaborated on last week, where we're going to look at how we find local extrema for functions of two variables. So what I'm going to do in the first lecture, so we'll probably finish early this lecture, what I want to do in the first one is review what you should already know for functions of a single variable, because it's crucial that you have a good understanding of what we do with functions of a single variable. Also illustrate some of the common mistakes that we see from people who have done this previously at school and things like that. All right, so with functions of a single variable. So this lecture today should all basically be revision, stuff you've seen before. Right, so we start with the idea of an increasing and decreasing function. So remember, the derivative basically gives us the slope of a tangent line. So we can use the sign of the derivative to tell us if the function's going up or going down. Right? So if it's going up, we say it's increasing. If it's going down, we say it's decreasing. Right? So where it changes sign is where it has either a peak or a trough, like a local maximum or a local minimum. Right? And the way we find it is, we all should know this, we find the first derivative, we set it to equal to 0, that gives an equation involving x, off we go and solve it. Right? Right, so at a local maximum, to the left the slope is positive, to the right the slope is negative. Imagine the slope space are going up, plateauing down, so it looks like this. Right? So it's a local maximum, or a local maxima. At this point we have the derivative equal to 0, the first derivative equal to 0. It'll be positive to the left, from your perspective, yeah, positive to the left, negative to the right, right? Going up, increasing to the left, decreasing to the right. At a local minimum, the opposite happens, right? So at a local minimum, it's decreasing to the left, increasing to the right, so we've got a local min, right? So where it crosses and where the derivative equals 0, right? So all of these points, in general, a local extremum of f is the value that f either has a local max or a local min, right? But not all solutions of the first derivative equal to 0 are extrema, right? This is the first common mistake. We call all the points where the first derivative equals 0 or is undefined, so it blows up, like so dividing by 0, that sort of thing, as critical points. So not all critical points are local extrema, but local extrema are critical points, if that makes sense. Right? So when the derivative equals 0, it's either doing this or doing something, it's either got a local max, a local min, or something else. Right? And usually we're only interested in the local max and the local mins, and sometimes inflection points. So you have to read the question carefully. If I ask, identify all the local, find all the local extrema, I'm asking you to find the critical points and tell me which ones are local maximums or local mins. That's all I'm looking for. If I ask you to find all the critical points, I want you to find me every single point where the first derivative equals 0 or is undefined. Okay? Right? And as this one shows, not all critical points are local extrema. A classic one is a horizontal point of inflection. Right? So sometimes what happens is the function, say in this case it might be increasing, it might flatten for a bit and then start increasing again. Right? So that's neither a local max nor a local min. That's just a critical point that we might identify perhaps being an inflection point or something like that. Right? So a local extrema is where the first derivative is 0 and changes sign. Right? If it doesn't change sign, it's not a local extrema. If it's blowing up, it's a critical point, but not a local extrema. Right? Right, and then from this simple idea, we have the first derivative test. Right? So everyone should know this one by now. Right? Suppose we've got a function that's continuous and differentiable. Everything we do is going to be differentiable. Continuous is another thing. There might be points where it blows up. And then it has a critical point where the first derivative equals 0. To classify that critical point, if the first derivative is positive to the left, negative to the right, it's going up, flat, down, local max. If it's negative to the left, positive to the right, it's going down, flat, up, local min. Right? If it doesn't do either of those, it's something else. right? And it's neither a max nor a min. So if it's the same sign to the left or the right, then it's neither a local max or a local min. And if a critical point where they blow up, that's nothing. That's not a local, certainly not a local extrema. It could be a global extrema, but certainly not a local extrema. Right, then we have the extreme value theorem. Right, so there are two things we can ask. Either I can ask you to say, find and classify the the local extrema of this function, or I could ask you to find the global maximum, the absolute maximum and the absolute minimum. Right, and this idea comes from if the function's smooth and perfectly well behaved, so it's not blowing up anywhere and its first derivative is not blowing up anywhere and it's basically nice and smooth and continuous like polynomials and things like that, then we have the extreme value theorem. Right, so let's say f is continuous and we're interested in some interval, say x between a and b. Right, if it's continuous, that means it's nice and smooth. So somewhere between a and b, because it's continuous, therefore it's not blowing up, you know, things aren't shooting off to infinity, there's no vertical asymptotes, that sort of thing, right, then it must have an absolute maximum and it must have an absolute minimum somewhere between A and B. Right? And if it's smooth and perfectly well behaved, they must happen either at local extrema or the endpoints. They can't happen anywhere else. I mean, if there was another point where it was happening, and of course this thing's not blowing up to plus infinity or minus infinity, there must exist a local max or a local minimum there somewhere for it to come back, right? Because it's not allowed to blow up, right? So basically for this question, if this was a particular function and I asked you to locate and classify the local extrema, you would say there are two. Right? There's a local max over here to the left, there's a local min over here to the right. However, if I asked you to find the global maximum or the absolute maximums and absolute minimums of this function, what you would do is I'd either give you an interval or the interval would be implied by the question somehow. Right? And if it's smooth and perfectly well behaved, then the absolute maximum and absolute minimum must happen either at the endpoints or at the critical point. So in this one, for example, this one is a local maximum, but is not the global maximum because this point at the endpoint is higher. Right? So the global maximum for this one would be this point, whereas this is a local minimum and a global minimum because this is lower than this one. Right, and I only have to check these 4 points. As long as the function's well behaved and doesn't blow up, you only check the endpoints and the critical points. The biggest is the maximum, the smallest is the minimum. Right, so to find it, basically you just follow these steps. Locate the critical points and identify, and also where f dash is undefined, but for global, the extreme value theorem, that won't usually happen. Right? List all the values. The highest is the maximum, the lowest is the minimum. Right? And it's either got to happen at the critical points or the end points. So you just sort of tabulate them and say this is the biggest, that's the max, this is the smallest, that's the min. But only if it's smooth and well behaved. Right, as an example, let's say consider the function y equals 2x times x minus 2 all squared, defined on the interval x between minus 1 and 3. Right? First thing I do is I find the derivative, so it's a relatively simple product rule / chain rule. Because I know I have to solve this, I factored it already. So remember what I've said, when you find derivatives, you don't have to, all I want you to do is expand and collect like terms, unless I specifically ask you to do something else. The reason I factored this one is I have to solve it. Right? And the only things I expect you to be able to solve are simple equations and quadratics and things like that. Right? It's not going to be like an order 37 polynomial that somehow I miraculously expect you to solve. Right? It's something you're already familiar with solving. Okay? Right, so I factor the first derivative. You see, when that equals 0, I either have x equals 2/3 or x equals 2. Right? Now, because this is a nice simple polynomial, I know it's smooth, it's well behaved, it doesn't blow up, no dividing by 0, no square roots are negative, none of that rubbish. Right? So by the extreme value theorem, I know that the absolute maximum and the absolute minimum can either only happen at these 2 points or the end points. Right? So it's either going to happen at -1, 2/3, 2 or 3. Now, if one of these critical points, say one of the critical points was x equals 10, I wouldn't give a crap, right? Because the question's asking you only between -1 and 3. So the 10 one, I don't care what it's doing out there. Don't care, right? So, and then all I do is I just tabulate them, right? So at the first endpoint, and I usually do them in order from leftmost point to the rightmost point, makes life easier, right? So at -1, then at 2/3, it's at 0. Oh, 2 equals 0, and 3 equals 6. So therefore, the absolute minimum happens at the left end. Highlight, you piece of crap. Right? Happens at the left end point. Stupid thing. And the maximum is, so 64 on 27. What's that? Obviously, you could use a calculator. Is that bigger than 6? Hell no. No. Why did it take me so long to figure that out? Right? So that's the absolute. Right. So what am I? Oh, I'm doing it the other way around. This is the absolute maximum. Absolute minimum. That's a local max, and that's a local min. Right, so it either happens at the critical points or the end points. Right, and here's a plot of it to prove it. Right, so obviously, you know, that's its absolute minimum, that's its absolute maximum, that's a local max, and that's a local min. Right? Next thing we have to do is concavity. Right, so recall that if we're at a local maximum, remember what the first derivative tells us is the slope of the tangent line. Now you can imagine that if you draw these, you can imagine what the tangent line's doing is it's positive but it's going down to 0, flattens to 0 and then goes negative, doesn't it? You imagine sort of the tangent line following the curve around as you go from left to right. And remember, of course, the first derivative is a function in its own right that also has a derivative. Its first derivative is the original function's second derivative. And notice it's going down. It's positive, but it goes down to 0 and then goes negative. So the first derivative is a decreasing function, which means the second derivative is negative, right? Because the second derivative is a rate of change of the first derivative, you know? Right, so if the second derivative is negative, then the first derivative is decreasing, so the tangent line basically turns clockwise from your perspective, yeah? So we say the curve is concave down in this case. Right? It's basically saying you're at a max and it's opening downwards. On the other hand, a local min, you can imagine the tangent line going from left to right, is starting negative, but then increases, goes to 0, and then goes positive. So the first derivative is an increasing function, which means the second derivative is positive. Right? So if the second derivative is positive, then we say the curve is concave up. This means that we can use the sign of the second derivative to tell us if we're at a local max or a local min. However, this is the first most common mistake we see, right? If the first derivative does not, if the second derivative is also 0, then we don't know what's going on. Right? And the most common mistake we see is you immediately assume that's an inflection point, which is not true. Right? An inflection point is where a curve changes from being concave up to concave down, or concave down to concave up. Right? So not only should the second derivative be 0 at an inflection point, it also must change sign at an inflection point. The easiest way to think about this is think about the function y equals x to the 4. Now we know that's basically like a parabola that's a bit steeper. It's not a parabola, but it's kind of, you know, you squint, that's what the frickin' thing looks like, yeah? Right, so it's basically some sort of cup thing. Now think about that function, x to the 4. Its first derivative is 4x cubed, that equals 0 when x equals 0. Right, so x equals 0 is a critical point. We know it's a min. The second derivative is what? 12x squared. Right? That also equals 0 at this point. Right? But it is obviously not an inflection point. This thing is always concave up. And that's because 12x squared is always positive. Right? So inflection points are where the second derivative also changes sign. And that's a common mistake we see. Okay? Right, so a simple example, think of x cubed. Right? Now we know what that looks like. Now its first derivative is 3x squared. That equals 0 when x equals 0. So x equals 0 is a critical point. If I want to then use this second derivative test, there's 3x squared differentiate again, that's 6x. So at x equals 0, I get 0 again. Right? So that's not telling me if it's a local max or a local min. But it is an inflection point because it's 6x. That means it's negative to the left, positive to the right. Right? So the second derivative is changing sign. So this function's changing concavity. It's going from concave down to concave up. Right? Whereas x to the 4 doesn't do that. Right? Right, so anyway, this is the second derivative test. Now, depending on the function, the second derivative test is easier to use than the first derivative test, but it depends on the function. Sometimes you'll have very nasty functions. When you differentiate them once, that's bad enough. You don't want to differentiate it a second time. The other catch with the second derivative test is it fails, whereas the first derivative test never fails. Right? As long as you pick a point not too far away, it'll work. Right? Whereas if the second derivative is 0 as well, then the test has failed, and in that case you need to revert to the first derivative test to properly classify what's going on. Don't make the common mistake that if the second derivative is 0, it's not a max or a min, it's an inflection point. Bollocks! Think of the example y equals x to the 4. That clearly has a minimum, doesn't it? Right? But the second derivative test is failing there. Right? So the most common mistake we see is that if you tell me that if the second derivative is 0, we have an inflection point. No, if the second derivative is 0, the test has failed. Yes?
Can you not use a third?
You can if you wish. If you've learned to do that, that's fine. Yeah, that's fine. But the main thing is that if you say test fails, don't say, oh, it's an inflection point, because that is not necessarily true. Right? You just say test fails, and if I want you to you go to the first derivative test, right? Because that will never fail. What we'll see with functions of two variables is we don't have a first derivative test. Can you think of why? Let's say you're sitting on some surface and you're at a local, some point where you've got some hump like a hill. Why would there be no equivalent of a first derivative test, do you think? And there's infinitely many directions to check. Right? It's like a limit question. Right? Function of a single variable, if you use the first derivative test, you just got to test left and right. Sitting on a surface, you'd have to test every possible direction, which you can't do. Right? Well, sometimes you can, but generally you can't. Right? So we only have a second derivative test for functions of two variables, and that has the same catch. It fails. But with functions of two variables, if it fails, we say, I give up. Right? We have nothing to fall back on. Right? You could plot it, or, if you really want to know. Okay? And the easiest way to remember which ones, I've been using this trick ever since I learned this at school, right? Because I have a shockingly bad memory. Right? Think parabolas. We know what they look like. Y equals x squared, that has a min. Y equals minus x squared has a max, doesn't it? X squared, the first derivative is 2x, the second derivative is 2, positive, min. Yeah? Minus x squared, the first derivative is minus 2x, the second derivative is minus 2, negative, max. That's how I remember which one's which. Yeah?
With the second derivative test, if we do the evaluating on both sides and find that implies that it's inflection point, we still just use that?
Yes, of course. Yeah. Now, the questions might be locate and classify the critical points of this function, full stop, for functions of a single variable. Then it is your choice whether you use the first or the second derivative test. Right? But if I say use the first derivative test on this thing or use the second derivative test, then there's a reason. Now, either I know the second derivative test is going to fail, or I know that the second derivative is too hard to find. Right? It's just going to be too much algebra. But in general, the choice is yours. right? But the catch is with the second derivative test, as I keep saying, if the second derivative is also 0, please don't make the mistake that you say it's an inflection point, right? Because we see that all the time. I've actually seen it in a book, you know, a high school textbook, where it says if the second derivative is 0, it's an inflection point. And, you know, no, it's frickin' not, right? It has to change sign, right? It's wrong. Right, so if the second, unless I specifically ask you to find inflection points, right? If all you say here, if the second derivative is 0, you say test fails reverting to the first derivative test. Don't say inflection point, because that's wrong. Yes.
So we actually have to write down test fails.
Yeah. Yeah. I'll show you. We'll have a look at some examples. Right. So let's have a look. Right, locate and classify the critical points of this function. Now, when I get you to solve things, it's things that we can handle, right? So, you know, I think for this, quadratics, simple equations involving, say, maybe perhaps exponentials and logs, that sort of thing. I'm not going to get you to solve order 3 or more polynomials without giving you a hint. Yes? Yes, that'd be fine. I'd be happy with that, yeah. Now, what was I saying? Well, yeah, right. Polynomials, I'm sure you've probably done it before, but I'm not going to get bogged down in this. As you'll see, when we start doing functions of several variables, right? I mean, these are quite, what's the word? Mechanical, right? The process it's a sort of set process, and as long as you can, I'm going to give you ones where solving the first derivative equal to 0, linear, quadratic, or simple things involving maybe exponentials, logs, or trig. It's not going to be anything you're not going to be able to handle. All right. One we'll see when we do functions of several variables, that is by far the hardest step. Actually, finding the critical points to begin with, right? Because they're almost never going to be linear, right? But we'll talk a bit more about that in the next one. Right, so here I've got an order 5 polynomial. Now, I've been kind, and it's got no x squared and x in a constant term, otherwise this whole thing would be ruined, right? Find the first derivative, right? Notice it factors and it's a quadratic, right? We all know how to solve quadratics, and we've got the quadratic formula if we can't use the trick. You know, remember the trick, if it's monic, if there's a 1 multiplying the x squared, well, it multiplies to give the constant, adds to give, always got the quadratic formula to fall back on. Right, so here the first derivative equals 0 when x equals 0, and we solve this quadratic. I just use the quadratic formula when there's not a 1 in front of the x squared. Find x equals -1 and 3 on 2. Right, so this one's got 3 critical points. Right? Then I'm going to use the first derivative test to check them. So I just pick points, right, to the left and to the right, and I always do them in order from smallest to largest. Of course, you don't have to do that. That's just habit, right? So I check -1 first, then 0, then 3 on 2. Right? And I pick a point to the left and to the right. You're always going to have your calculator handy, so you can pick a point as close as you like. You could have picked -1.1 and -0.9. The value is meaningless. All I give a crap about is its sign. Right? The catch here is don't pick a point that's too close to the next critical point. Right? So you notice here I've got critical points at -1 and 0. Testing to the left and to the right, well, to the right in particular, I don't want to be anywhere near 0. Right? Because I know something weird, something else is happening there. Right? So close. Right? That's what we mean by the word local, close. Right? But I've picked -2 because nice whole number, and -0.5 because I don't want to get too close to 0, and I can reuse it for the next bit. Right? So at x equals -2, I discovered that the first derivative is some value. I don't care what its value is. All I care is it's positive. Right? So to the left, it's positive. To the right, it's negative. That means it's doing this. Right? So that's a local max. Right? And that's how I draw it in my solutions. At x equals 0, you've got to the left it's negative, to the right it's negative. Neither. It is not necessarily an inflection point. More tests would be required. And I didn't ask you to do that. Right? All the question said was locate and classify the critical points. Oh, well. Now that I think about it, it's a bit... Yeah. Let's say this. Unless I specifically ask for inflection points, don't do it. Right? So all the answer I'm looking for there is neither. It's neither a max nor a min. Right? And leave it at that. 3 on 2, left and to the right, it's doing this. Right? So it's got a local max at 1, a local min at 3 on 2, and something else at 0, I don't know what. Probably an inflection point, but I can't confirm that without doing more tests. And because I didn't specifically ask you to, don't worry about it. Right, find the global extrema of this same function between x equals minus 2 and 1. So I've already found the critical points. The critical points were minus 1, 0 and 3 on 2. 3 on 2 I don't care about, right, because I'm only asking between minus 2 and 1. Right? Obviously this is a polynomial, it's nice, it's smooth, it's well behaved. Extreme value theorem says the absolute maximum and the absolute minimum either happens at critical points or the end points. Right? So all I do is the first end point, I do them in order. The first end point, first critical point, second critical point, the right end point. Notice 3 on 2 I don't care about because it's outside the interval I'm asking. And I just evaluate the function at all of those. At minus 2 it's minus 176, at minus 1 it's 7, 0, 0, 1's minus 17. You're always going to have your calculator, of course. Right? Obviously minus 176, that's the global minimum. And 7, the global max. Okay? Use the second derivative test. Right? So redo question 1 using the second derivative test. Now I need the second derivative. Right, the critical points, I've already found those. Second derivative test at x equals 1, I find the first derivative is some negative value. Its value is meaningless. All I care about is its sign. Right, so I just say less than 0, max. Again, which one's which? Think of it like minus x squared. Second derivative is minus 2, negative, max. Right, that's how I remember. At the other one, 3 on 2, I get the second derivative is positive, it's a min. So that agrees with question 1. Notice at x equals 0, I get the second derivative is 0. All I'd say is test fails, right? Unless I specifically ask you, find inflection points, all you got to say is test fails. But don't say, oh, 0 is an inflection point. It might be, but you can't know that yet, right? Now I'm going to ask you, determine inflection points. Right, so inflection points are where the second derivative equals 0 and it changes sign. Right, so possible inflection points are x equals 0. When I solve this, this is another quadratic, not particularly nice numbers. But what you can show is that all three change sign to the left and right. Switch to decimals for this one, of course. Right, I have no idea what that is in decimal. I can't do that in my head, but whatever it is, what would it be? It'd be, I don't know, it's about what? 16 is 3 plus, what is it? Whatever the hell it is, right? Pick a point to the left and right, you can show that the second derivative changes sign. So it has 3 inflection points. But the key is that I've got to check a change sign, or there is a thing called the third derivative test, right? But the catch with the third derivative test, if the third derivative is also 0, then you need a fourth derivative, and it gets stupid. Right? So usually we don't bother with a third derivative test, just check the signs. But you only worry about inflection points if I specifically ask you to. Right? So the main thing is a couple of common mistakes we see from school. This is all stuff you should have seen before. Values where the first derivative blows up are also critical points. Not that we can do anything with them, but they are critical points. Right? Obviously they're not local extreme, they're potentially global extrema. They're probably the worst questions to deal with. If the second derivative equals 0, do not immediately assume it's an inflection point. Right? You would say test fails, or if you're using the second derivative test, you say test fails, revert to the first derivative test, where the first derivative test will confirm it's neither a max nor a min, or will confirm it is a max or a min, right? Obviously, when you do these questions, you don't have to do both the first and the second derivative test. Unless I specifically tell you which one to use, the choice is yours.
With the first derivative test, in the case where you had it was like neither, and the first derivative was equal to 0, however, on either side they were both decreasing, what could that be besides the inflection point?
For smooth functions, they will be inflection points, but for other functions, they may not be. We have to be careful, right? So to make sure, we need to check the sign of the second derivative, right? For well-behaved functions, yeah, they are most likely inflection points, but there are functions where it's not.
In this course, will they always be inflection?
No, well, again, think of y equals x to the 4. Right? That's a classic example, a simple example where the first derivative test works, right, but the second derivative fails, so you revert to the first. That'll tell you it's not an inflection point, so you have to be careful.
No,
right?
I mean when you use
if the first derivative doesn't change sign, yeah, it's always going to be, yeah. Okay? But unless I've asked you, don't worry about it. Just say fails or whatever. Yes?
Would you be wrong with 3 plus minus 2 or 1, because that's technically, when it's positive, it's actually outside of the domain of the interval?
No, this question didn't have an interval.
Oh, okay. So the interval only if the first.
Yeah. All right, so now getting grips to functions of several variables, we need to know all of this, right? So this is probably stuff you've already seen before, but please make sure you practice on these examples, and it'll make life much easier when we start doing functions of several variables, okay? Don't forget to have a look at the sample test, right? And remember my consultation Wednesday 9 till 12 if you need some one-on-one help, all right? I'll see everyone tomorrow.